Let's continue our morning session. But I want to point out that tomorrow we will be in the cross center where we were last year, the cross center for chemical biology. So this is closer for the department. So we're building just behind, we're building behind the fountain in the hometown. And so we'll start tomorrow at 9. So there are some small changes to the people here the right. So we'll get a talk by Donagi now, and the talk by Amanda Kirsten will be on January 31st at 9 a.m. in the morning. I hope there aren't other changes, but I cannot promise. Dennis?
Those that are staying in the courtyard area, but those who are tomorrow. So don't think that, oh, the bus brought you they to go to the crowd.
The bus will take you to the road, but the people who are in the thesis still need to go there on their own. All right, so it's a great pleasure to introduce Donagi from UPenn. He's going to tell us about explications what is this supersymmetric form?
Thank you again. So it's wonderful to be here. And I was just for breaking back great talks about the theory. This thing this is a big concrete piece. So this is work in progress with Victoria said. And project based on previous work with Argyres, Travis Sloan, Pennsylvania, and the soil in Argyres. So I could present origin for mixed physics and project. So I just quickly physics pretty quickly and get to the math. So some of the most studied quantitative theories we mentioned 4 and have an good symmetry. And among those, the most important ones, of course, are superconformity. And the other supersymmetric quantitative theories are interpreted as the formation of the superconformal. So we're going to have complete symmetric models. Major problem because we to understand and quantify possible geometries more than space and vacuum is beautiful. So these come into types, Coulomb branches. The Coulomb branches and well, and physics is foreign ability to just speak. Remember that we have a Coulomb branch and Higgs branch. And we see this specifically. So mathematically, we're dealing with integral systems. You will be more the Coulomb branch. The Coulomb branch is going to be a special game. It is in phase, and then people transfer from the integral system. So that B will phase and the phase. And it has a symmetric formation. In the projection path, in the quantum revolution. And often, this is happening from there by B observed curves. So the point B becomes the curve, system B, and the function is going to be the Jacobian or print variety of that curve. So that in general, the general fabrics is going to be the print variety of convex source algebraic structure. In the base of the co-dimension 1 locus in the Python, which is the discriminant parameterizes those files that are not real varieties. And physics another basic physics that's right there on the screen. So a lot of the story goes back to the work of Seiberg and Witten, one of the paper in quality, and a follow-up paper on monopoles. In those papers, they can work out basically by hand the theory for structure of SU2 with 0, 1, 2, 3, or 4, and then a mass or one entry. I wrote the paper with Witten where we extended that to SUN one of them. And in the paper, we basically described the connection between the systems and the connectivity. So there are two things that I often quote: the rank. So physicists often use the word rank to refer to the coordinate dimension B. B is usually a convex vector space. So that R be the dimension. There's also a group, and the group has a rank. So it doesn't confuse yourself. Whenever I talk about rank, I'm trying to specify which dimension. So for example, for any supersymmetric gauge theory with group G, how is going to be the rank of the group G? But in general, if you have a group with particles with masses, the two ranks will be different. So one thing that comes into this story is the Taylor symmetry. So the algebra of symmetries of the Higgs branch. And mathematically, it's a little opaque. So it's an end of the algebra that somehow comes into the picture. And it has the property that the formation parameters or the masses of the particle are going to live in the rectangle at the algebra, the plate of the algebra. So try to make sense of this in the top. So there's a series of papers by Argyres and his collaborators where they attempt to classify the rank one theory. In fact, they succeed. There's a series of these papers. And in a slightly different direction where they expand them. So, as I said, the goal is to classify the superconformal field theories and the superquantum field theory formation. So they went through two heroic efforts, and they managed to give a complete classification. So a couple of the issues are that for the conformal theory, you have scalar invariance. So that means that the discriminant, so the base is one-dimensional and the discriminant is a finite number of points, but it can only consist of the origin, because that's the only point that's scalar invariant. We have unique similar path. And therefore, with that classification of the generation of the curves, gives a complete answer for that case. So this is Kodaira's table. Probably a little bit small to read, but there's an I0, which is a smooth elliptic curve, the IN, which are n-gons, and there are cuspidal curves, triangles, and so on. And then there are three theories at the bottom, which are yours of 67 and 80. So correspondingly, here's the table of superconformal field theories in rank 1, found by Argyres and his group. So you'll see that not all the types appear, but most of them do. So in each case, you hear me now? Not sure what happened. What? Better now? Yes. Thank you. Okay. So this is the table of scale invariant theories that they get. I guess I'll explain how they get it in a minute. The more general Coulomb branches are going to be deformations of the scale invariant one. And the deformation parameter for this is called the mass of the particles. So the full family is going to form a Poisson system. That means we have Poisson manifold with a Lagrangian federation to a base. On the base, there are some functions that are usually called Casimir. If you fix their value, that fixes the symplectic leaf of the Poisson system. And above it, you have an integrable system. So above zero, you have the original conformal theory. And the other theory is level with non-zero values of the Casimirs. So fixing the masses of the Casimirs gives it symplectically. The Poisson system is still scaling invariant. There's an action of C star which we scale massively. But non-zero leaves themselves are not scale invariant. Obviously, because the point in the base is not going to be invariant. So roughly what's happening is that at time zero, you have a very similar fiber at the origin. And when you deform it, you see it splitting into a simpler similarity. And then the question that the physicists were addressing was which patterns of deformation actually come from physical theories. So they list several physics assumptions, some of which make sense to us, some are very mysterious. They want rank one, they want the Coulomb branch to be planar, which in this case is the base is a complex line. The massive theory is the deformations of the massive theory. There's something they call the safely irrelevant conjecture, which says that there are no dangerously irrelevant operators. I spent a lot of time trying to understand it and did not. But it imposes constraints on the singular fibers that can occur in those conditions we do understand. And they have other conditions knowing the theories and discrete case flavor and so on. And finally, there's one condition which they call the quantization condition, which says that if you have both an IN and an IM fiber in the same system, then the ratio has to be a perfect square. You can have an I2 and an I6, you cannot have an I2 and an I5. Which seems a little weird, but that's what they need in order for that direct quantization to work in order to get integration. So under these assumptions, they classify all possible Coulomb branches and they get a list 28 types. Then they show that each of these arises from the family of genus 1 spectral curves and several Witten curves. And they construct explicitly several Witten equation. And they go case by case and show that all of them actually arise from conformal theory. This is their list. Go down 28 items. the first column, the one that says SQFT singularity, tells you what fiber at zero, what kind of elliptic fiber lives over zero in the underfold. So if it says 2 star in the first batch, that means that the fiber at infinity is going to be 2 without the star, which means it's a pass. If you have a 3 star at zero, that means that at infinity you have type 3, which is attack node and so on. And in each case, they list the deformation pattern, which actual fibers exist in the first row. You have a 2 star fiber for the conformal theory. For the general deformation of it, you have 10 nodal curve, 10A1. In the maximum flavor symmetry, this is the mysteriously algebra called the flavor symmetry. Is listed. So in that first case, it's the 8, and then it goes down from there. So there are 3 lines, number 3, 6, and 8, that are outlined in red. Those are the ones for which they do not have an actual physical theory to realize them. For type 3, they can show that there is no such theory. For the others, they think there should exist, but it's not known. And the last comment asks whether a particular construction of these things is known to theories of class S, and I'll talk about those towards the end. There's also a twisted version of this, where they remove one of their assumptions. One of the assumptions was that there was no discrete part of the symmetry. They were fine consistently of relaxing that assumption. So they get a somewhat enlarged, it's a finite set of possible. Okay, so what does this mean in algebraic geometry? They're really studying rational elliptic surface. So that's the smooth surface is S, fiber of P1, with a section such as the generic fiber in elliptic. Equivalent to S is the blob of the plane at 9 points, and they have to be the base point of the pencil of cubics. You can write a similar recipe as a Weierstrass form. And back in the 70s, I think, or maybe early 80s, was Persson obtained a complete classification of 4 rational elliptic surfaces in terms of the possible configurations of singular fibers. And this was refined and simplified by Witten and Miranda shortly thereafter. The list consists of 289 configurations of singular fibers. So it takes some work. So some of the criteria that Witten and Miranda used. So one condition is that the Euler number has to be 12. The contribution to the Euler number of each smooth elliptic curve is 0. This just gives you a condition on the possible configuration of elliptic of singular curve. The Picard lattice itself has to be embedded in the largest possible Picard lattice, which in this case is going to be E8. So the sum of the ranks associated to each of the single fibers has to be at once 8. In fact, there's a little lattice associated to each of the fibers, and the direct sum has to be contained in the E8 lattice. And there are some conditions on behavior with J map. So if you have an elliptic surface that gives you a map from the base to the J line. And you can impose some natural conditions on the ramification behavior of that. So this J map just sends the point of the base of the J invariant of the hyperweight. It deals with the degree in other words, the number of poles of J. And then you go through the list and you see that the only types IN and IN star have poles. So that gives you this particular equality that the sum of the IN and IN stars has to be equal to the degree of the J map with the corresponding single file. So for example, if D equals 0, that means the J map is constant. That's it, all the fibers of the same J value. And numerically, this implies that when D is 0, the J invariant corresponds to an automorphism over the 4 over the 6. That says that the first case arises only from type 3 and 3 star, the second arises from the other fibers. So it's conditioned on the numbers of fibers. So using these application properties, Miranda comes up with a very complicated formula which constrains the possible numbers of fibers. And then he just goes ahead and looks at all possible partitions of number 12 into fibers. And here's the table he gets. So the first column gives you the degree of the J map. So if you look at the second item on the first row, there's 2 star and 2. So this is one of the fibers. This is one of the surfaces that have this 2 singular fibers. So the type 2 at one point and type 2 star at the other. The order characteristics add up to 12 they should. So see there are 3 of those. There's a 2 star 2, there's a 4 star 4, and somewhere there's a 3 star 3. So these are somehow the simplest possible rational surfaces. And then this is the beginning of the table, continues for another page. And the degree of the J map can go from 0 up to 12. In each case, he has a complete list of all the possible configurations. Okay. So, how do you relate rational elliptic surfaces to superconformal field theories? The classification showed that the 4 surfaces having only 2 single fibers. I pointed them out that we were going to. You can have an 0 star and 0 star, or 2 and 2 star, 3 and 3 star, 4 and 4 star. So this was known in the method literature before that. People reveal, for example, natural point this out. The 7 scale invariant branches, if you remember that the table that I displayed, obtained by removing 1 singular fiber of 1 such surface. To take one of these surfaces, you pick a fiber, call that the fiber at infinity. The complement maps over the affine line. And that gives you the integral systems that give rise to the conformal field theories. And for the quantum field theories, you get the deformation of the scale invariant. That too is going to be the affine part of some rational elliptic surface. You have to work out the possible deformation. And conversely, since the fiber is an anti-canonical divisor, any such affine surface is going to be homomorphically symplectic. It will give you an integral system. So I gave you a long list of physical constraints, which I understand only partially. So we extract 3 mathematical consequences from those. One is that the fibers over infinity, the fiber must be singular, and it's one of 7 possible types. So they have some reason to exclude the others. The second condition is the fibers of a finite value of U must be of some other list of types. Basically, they have to be the IN or one of the star fibers. And the third condition is the quantization condition that says that if n and m both occur, then the ratio has to be a perfect square. We apply this condition one at a time to the long list of 289 surfaces that Miranda and Persson found for us. This again was the original list. So let's mark in red all those where the second condition is violated. Okay, so we eliminated a lot of things on the first page. So then we had in green the ones where the first condition is violated. So there are a couple of extra cases that are erased in this stage, and a whole bunch towards the end. And then when doing blue, those cases where the third condition is violated. And then a few cases are left in black. And you count them, and there's 28 of them. And it's exactly the list that the physicists are telling us about. Okay. Well, actually, quite a bit more is known about the family of elliptic surfaces. How am I doing on time? One thing worth studying about each of these rational elliptic surfaces is the Mordell-Weil group. So that defines the group of sections of the elliptic fibration. It has a natural pairing called the height pairing, binomial form on it, integer value. You define the neo-Mordell-Weil group to be the subgroup. Those sections that meet each single fiber on an neutral component. So the fiber is irreducible, there's no condition that the fiber has several components. Then the neo group allows only those sections that hit the neutral component. So tell them this is always a lattice, and the full Mordell-Weil group, the direct sum of two pieces. One is the dual of this neo-Mordell-Weil lattice, the other is the total part, which is the final group. So Oguiso-Shioda worked out all possible Mordell-Weil groups, as well as the neo-Mordell-Weil groups for rational elliptic surfaces in terms of the fibers, single fibers. And they get another long list, something like this. So if you look at number one, the neo-Mordell-Weil group, that's the thing that they call EK0, is going to be E8. The lattice is E8, and so is EK. So this is the case where you have a bunch of I1 factors, the most generic case. And then the more structurally imposed, the higher singularities of the fibers, the smaller the Mordell-Weil group becomes. The first bunch tend to be either root lattice or weight lattices, but further down the list, you see that you just get random looking matrices that give you the Bellman form. This is the end of the data. So the flavor algebra of this from field theory govern the possible deformations in the sense that the last parameters that are just given by the Karayayla effect. So the parameter is deformation, so that you're preserving the pattern of similar fibers. In general, the unconstrained deformations of a rational surface are given by E8. So if you start with a plane and you draw up 9 points, you get something where the count group is rank 10. You look at the sum the sublattice of things that are perpendicular to the fiber in the zero section. That will have rank 8. It turns out to be the 8 lattice. If you have a more interesting rationalistic surface with a lot of singularities, then you can still look at the Picard group of S, and again, you take the perpendicular to the zero section fiber, and that gives you the flavor algebra. So the statement is that the formation preserving the pattern of singular fibers are going to be the perp of the zero section and fiber components. So the families of algebraic and inverse systems are indeed labeled by deformation parameters, which live in the complex vector time of this flavor algebra, which is basically given by the Mordell-Weil lattice.
Sorry.
Yeah.
Can you show me once again the list of the length of the Mordell-Weil lattice? Like, yeah, 2 slides ago.
Doesn't want to go back. This one?
Yeah, so is the length of the Mordell-Weil group bounded in this case?
The question is whether the rank is bounded in this case. The answer is yes, it's bounded by 8. So you get, so in general, the Mordell-Weil group is, you can start with a plane, block 9 points. Some of them might be infinitesimally close to each other. But that gives you your surface. And then the Mordell group is given by the perp in that rank 10 lattice, the zero section, and all the components of all the fibers. So it's perpendicular to at least 2 classes, therefore the rank is at most 8. Any other questions? So the Karayayla classified all cases where one rationalistic surface can be a cover or a quotient of another. And again, you get some finite list of possible cases. In each case, you list the singular fibers of one surface and singular fibers of the other. I forget which is which. So it goes for a while. As pointed out by Coulomb and Chakotay a couple of physicists, this turns out to be the key to a complete classification of what the other group of physicists call the expanded landscape. So this expanded landscape over allowing finite groups in the symmetries. And geometrically, that means that instead of working just with the rationalistic surface, you work with a pair of rationalistic surfaces, one of them covering the other. And it takes a look at the variant piece of the theory that you get. So one way to construct conformal field theories is to start from a 6-dimensional theory And those depend only on discrete data. You just specify the algebra of type A, D, or E. And compact by to four-dimensional theory, the commodification depends on the function Riemann surface. The Riemann surface is two-dimensional, so it reduces the dimension from 6 to 4. And this is imposed defect that at a finite number of points we divide with D in the curve C. Mathematically, this defect is specified by an input coordinates class in the relevant algebra G. So the master integral system that governs such classes theories is the Markman homomorphic or Bottachin integral system. So it parameterizes all normorphic Higgs bundles where you fix the base curve, you fix the points of the divisor. You look at normorphic Higgs fields, which first order poles at those points with the residue in the given input in the specified input coordinates class. The third space H is the moduli space of Higgs bundle, V phi on the curve C. Phi has both the point D and the residue in the specified coordinate class. And this H turns out to be algebraically symplectic. So this is one powerful method for constructing such models. Characteristic polynomial phi determines the branch cover, theta to C, which is the spherical curve with the subweighted curve. The Coulomb branch B is the moduli space of such cover. Right, together with the value now to the total space, the twist canonical. The HMF sends a Higgs bundle, so a G bundle and a Higgs field on it, because it's a polynomial of the Higgs field. The mass deformations are obtained by allowing the residues to take values in a sheet containing the specified importance. So the conformal theory corresponds to one importance. Now you want to know how can you deform it? So you want to deform each important element to something that's not important. The problem is to decide which of these deformations are continuous. So a sheet in the algebra is the following. You fix an integer, you look at all orbits, all conjugacy classes that have that dimension. So you look at their union, you take a irreducible component of that, you call that a sheet. So it's basically a way of deforming a given class to other classes that have the same, and not centralized with the same form. So the sheets control the mass deformation that you get. The sheet is a irreducible component of the union of origin orbits fixed dimension. So some of the rank ones for conformal field theories are known to derive from specific class S construction. So if you remember the table that I displayed, this is table, the one who saw the colors. The last column had check marks on some of the theories. So those are the ones that are known to arise from class S. So for example, this holds for the four maximum theories, which are the singular fibers of type I1. So in each of the batches that we had, the first theory listed had some interesting fiber at infinity and boring fibers everywhere. So those four theories can arise from this thing. Situation for most of the other theories are still unknown. So one fact that might be unexpected is that there are only finitely many possible normorphic Higgs systems that have rank 1. That means I'm allowing the vector fund to have arbitrary rank, and I want the base to be one dimensional. So the integrable system is two complex dimensional. And here is the list of vector produced. So you see that smallest possibility on top involves rank 2 vector bundles. And the 2 just says that we allow arbitrary conjugacy classes each of the 4 points. This gives you an idea of a star. And then you have theories in rank 3 and 4 and 5 and 6 and so on. Each of these theories has, when you work out the integral system, it has just one base parameter and one hyperparameter. And the number in the last column gives you the minimal mass deformation. So the first theory really depends on 6 parameters. 4 of them are massive, and the remaining 2 parameters a fixed theory is fixed answer. And you see that the list goes on for a while, but then it stops at 14. So the claim is that this is the complete list. So the other claim is that these do not produce any non-axial theories. So all of these theories, all of these hidden systems produce only the 4 theories repeated again and again. So if you want to prove that, the idea is to use 3-dimensional symmetry, which allows you to convert the hidden system to a dual quiver theory. The way you do it is you create a star quiver in the center node, and for each of the branch points, for each of the points that divides with D, each of the points of the X field is allowed to be homomorphic, you have a branch. And along that branch, you put a sequence of nodes, which basically correspond to the number of columns in the Young diagram that gives it quotation. So in nilpotent in type A, for SLN, in nilpotent is specified by a Young diagram. And basically you look at the transport Young diagram and you count elements in the row and get a quiver. There's a process called rebalancing a node. It corresponds roughly to performing a middle convolution on the system. There's going to be a middle convolution to reduce the rank. So here's what these things look like. So let's start on the bottom left. So this is an example of a rank 6 theory, where I have 3 punctures. Each puncture is described by a quotation of 6. So one puncture is of type 3, 3. The other one is also, oops, something's wrong here. This is supposed to be a rank. This is supposed to be an SL8 theory, and there's a typo there. So let's start with another one. Let's start with the one above it. So that's an SL7 theory. The quotation is 4, 3, 3, 3, 1, and 3, 2, 2. So you reshuffle these numbers, and you get this quiver that describes the theory. So it starts with 7 at the center of the star, and then the numbers go down in each direction. And then you look for balance. So if you look at the number 3 on the horizontal branch, it's exactly the average of the 2 numbers around it. So 1 plus 5 is twice 3. So the 3 is balanced. The only number that's not balanced in this particular diagram is the center, where you have the 7. Because the numbers connected to it are 4, 4, and 5. You do not forget what is 8 plus 5 is 13, which is smaller than twice the 7. So that says that the 7 is unbalanced. So you rebalance it by replacing it by a 6. And you also reduce each of its neighbors by 1. So you have the diagram. I wish I had the pointer. To start from the bottom, go up 1 over and 1 over to the right. So the 7 became a 6, and its neighbors also became reduced. And you ask, is this one balanced or not? And it turns out to not be balanced, so you keep flowing, and you follow this diagram. At the end of the day, you're in the upper right corner, and you recognize the affine linear diagram of I0 on D4. So the point is, well, there are 2 points. One is that as you flow, you're not changing the number system. You're changing its representation. You're reducing the rank of the algebra, but you're not changing the actual symplectic manifold you get. So the fact that you can start from any one of these theories up to rank 14 and flow from it and get down to the 4 basic theories, these are the only theories you're going to get from this process. So here's the picture of the flows for E7, and here are the flows for E8. So basically what we've done is we went through the list of all possible SLN theories that are one-dimensional, and we showed they're all connected by this reduction, by this little convolution operation. And the similar argument can also be used to prove that the classification is complete. In other words, that beyond 14, there are no such one-dimensional theories. Because if there were a theory in dimension 16, it would have to flow to some other dimension 15, and so on. So we just do a computer search, which Victor did, and found that there's a unique example in rank 14 and none in rank 15. And therefore, you also know that there are none in higher ranks because they have nothing to float. So, where are the remaining theories? So, a few of them occur as Hitchin systems of times D and E, and a few more occur as twisted Hitchin systems of times. In other words, they correspond to those theories of Karayayla. But most of the known theories actually arise from wild Hitchin systems. So until now, I was only talking about the tame case, which means that the divisor of D is reduced, which is consists of a bunch of points, and we allow first order pole at each point. Now you can start allowing points to coalesce. And then instead of first order poles, you have high order poles. And turns out you can do that in a way that degenerates your generic rational elliptic surfaces to more interesting. So for example, each of the final base systems gives you one of its examples of a rank 1 theory that is realizable by a wild theory, a wild Hitchin system, but not by a tame one. And what continues on identifying the rank 1 superconformal field theories of rank S in the other types, with and without twists, and especially the wild one. I still have a couple of minutes. So let me just mention some related results. So I've been working with Jacques Tesla, Ashwin Balasubramanian, and their students. So we have one paper on family diffusion systems and N=2 theories. And in it, motivated by the connection to for the N=2 theory, we studied the global behavior of families of thinly ramified H-interval systems. When you allow the underlying curve to vary, or what the minimum for motivates NG bar, or stable point curve. So in particular, we construct a vector bundle over mg bar with fibers over mg with the unquantified moduli space of the corresponding Hitchin base. So in other words, we're trying to understand what happens if you allow the base curve to degenerate to something in the boundary of the minimum point. Turns out that the naive extension is wrong. The naive formula for the base is given a direct sum of global section of powers of some twisted canonical bundle in its powers. That does not give you a vector bundle, it gives you a coherent shape that jumps rank. So you have to modify that and construct the correct extension, which gives you a vector bundle over the minimum. We also have so the first paper was in type A. There's an analogous study in type D, where all kinds of new phenomena occur. So again, the idea is to study the theories of class S. In order you need to understand the image of the H map in the image system of type D, with residues in a special important orbit. We describe two important features that distinguish it from the type A case. So one feature, which we term even type constraints, arises if the partition label has even parts. The partition label is the partition that describes the given input. In this case, the H image is non-singular, and therefore it's different from the one satisfied by Island Kamagapoor. So it turns out that in this type D system, it's not completely clear what you want to take as the base. So there's a singular model that you can get, and there's a smooth model which turns out to be its partial resolution. So we argue that our Hitchin image always globalizes to being the Hitchin based interval system. Second feature, which we term odd type constraint, is related to a particular finite subgroup of loose six canonical portion group being non-trivial. And that's related to the possibility in type D that through a given important, there are many different sheets that intersect there. In type A, that does not happen. In type A, if you have an important, there's a unique sheet, a unique way of deforming it, keeping the dimension of the orbits. In type D, there's this Lustig group which describes components. The choices for the local Hitchin base are in bijection of subgroups of this group. And much of it depends on the existence of generalized Pfaffians. And the next paper, such as that conjecture, so the determinant of an anti-symmetric matrix, as we know, is the square of the Pfaffian, which, like the determinant, is a polynomial in the entries of the matrix. Studies of sediments of conformal field theory suggested the conjectural generalization of this, predicting that each of a series of other polynomials in the entries of the matrix also has a polynomial square root. Among other consequences, this conjecture led to characterization of the local Hitchin image for type D, which is what happened in the previous work. There were important special cases established previously. In this paper, we proved the conjecture in full. separately does the work with Andreas Herrera, where we lift the type A construction. So in the table with the physicist, we constructed a vector bundle over the manifold MG bar, which gives us the basis of the hypothetical agent system. So here we actually construct universal Higgs moduli space. So the universal partial compactification relative modulated space of semi-stable normalic bundle over the stack of stable point curves. Parameterized normorphic Higgs bundles. And it's equipped with flat and proper extension into usual agent. Over an open subset of the agent base, parameterizing allowable nodal spectral coverage, we describe the relation of the phi with the compact vector covariance. And thereby we establish an analog of the Boolean equation. We also constructed version of the moduli space where we require the residue of the normorphic Higgs bundle to lie in a given set of network conjugate classes. In flatter case, we show that there is flat and proper hegemorphism to the flat degeneration of the corresponding family of agent bases. And finally, there's a more recent paper where we do further study of the type D theory. So, thank you very much for your attention.